Hello, welcome to today's video on proof. Specifically something I guess you could call proof by deduction, but it's worth mentioning in the Maths A-level exam, I don't think they're ever going to refer to it as, specifically, proof by deduction, this thing. They're just going to say proof, because in general, this is really just using just general algebraic reasoning to prove whatever it is you're trying to prove. And what we're going to try and do is I'm going to try and show you six, maybe that's too many, I don't know, 6 examples of how to do this stuff, and that will hopefully give you a good idea how to approach these questions. So before we get going, a couple of very key facts that are going to be really useful for this, for these proofs in general. The very key fact that we're going to use the most of all is the fact that any number squared, if it's real, is going to be greater or equal to 0. And that's just something you're allowed to quote. You don't have to justify, but quoting this fact is going to be very useful. And then other facts that are going to be useful are things like, obviously just having knowledge of how multiplying and dividing positive and negative numbers together works, all that sort of stuff. Anyway, let's launch straight into the first example, because that fact of something squared being greater or equal to 0 actually means we can start proving some things very easily. Like, for instance, this first thing, x squared plus 6x plus 9 is greater or equal to 0, just because if you factorize the left-hand side, you realize you've just got x plus 3 all squared, and that's guaranteed to be greater or equal to 0 because, well, any number squared is greater or equal to 0 if it's a real number. So that's all you basically got to do. Got to point out that x squared plus 6x plus 9 is equal to x plus 3 all squared, as x plus 3 all squared is greater or equal to 0. Therefore, x squared plus 6x plus 9 is greater or equal to 0. For all real values. By the way, I haven't done that for any examples. I should point out that this is only true for x is any real number. Second one, how do you prove this? Well, this is where other key skills start to come useful. Things like completing the square, because the whole point of completing the square is to rewrite for instance, a quadratic in a form so you can show it as something squared, then plus or minus a number. So, for instance, if we were to start off by doing a bit of algebraic work, we can see that we can rewrite this using completing the square as x minus 4 all squared, take away 16 plus 18, which of course is just x minus 4 squared plus 2. And then that's useful because we can justify that this is going to be greater or equal to 2, because we can start off by justifying that x minus 4 all squared is greater or equal to 0, because anything squared, if I can write stuff properly, greater or equal to 0 for any real number. Therefore, if we add 2 on, it's going to be greater or equal to 2, and therefore we can say that x squared minus 8x plus 18 is greater or equal to 2, because x squared minus 8x plus 18 is equal to x minus 4 all squared plus 2. Notice what I've done here as part of the proof. I've tried to really guide the person who's reading this through the logic behind what's going on. I've started off with a simple fact, which is that something squared is greater or equal to 0. Then gone, well, what happens if we alter that? What would we get? And then, that then gives the justification for why this other thing is greater or equal to 2 as well. So that's the basic idea behind the very simple ones of these. However, they do get a bit more tricky. You can get things like this. However, it's not all bad, because we can use a little trick to help us with these things. Because technically, we're not meant to be working on both sides at the same time. Even though I was sort of doing that before, I kind of wasn't, because I was just doing that in the justification, really. So I wasn't really ever working on both sides at the same time. So therefore, for this one, how would you do it? The problem is that thing's not going to be very nice to complete the square. And even if you do, you're going to have a problem, because you'd only be able to show that that quadratic is greater or equal to a number, not that the quadratic is greater or equal to some other algebra. So to help prove that, what the first thing we're going to do is we're going to go, well, it's much easier to prove if the quadratic is greater or equal to a number. So we don't want that 3x on the other side. Except, as we don't really want to be working on both sides at the same time, a little trick we can do is as follows. I can say, well, I know I'm not technically allowed to work on both sides at once. I'm still got to do stuff only to x squared plus 17x plus 71 without doing anything to the right hand side at all. But I can get around that by going, well, if I was going to work on both sides at the same time, I could take away 3x plus 22. And normally you'd be doing that to both sides. But because I'm not working on both sides, what I can do is technically only work on the left-hand side by immediately adding on 3x plus 22 back on. By doing that, I've technically done the equivalent adding 0 to the left-hand side. So I've technically done nothing. So therefore it's legal. But also, therefore, I haven't altered the right-hand side because I haven't done something to both sides. I've just stayed on the left-hand side and done something that hasn't altered it. Therefore, what you're going to do after doing this little trick is what this little trick will do is it means I'm going to have a 3x plus 22 present in all my lines of working. I'm not going to do anything to that plus 3x plus 22 because I'm expecting that to be left as almost like a remainder left over from any of the lines of working I do. And I'm only going to sort of use this minus bit, the bit that I would have normally got from working on both sides, but haven't obviously done here. I'm going to just absorb that as part of my working and just leave this thing almost sort of separated. So if I do that, then I am going to have, okay, we could just do a bunch of algebra here. Minus 3x minus 22 plus 3x plus 22. Then absorb the minus 3x and minus 22, so working on just this sort of stuff. X squared plus 17x plus 71. Except, sorry, we've taken away the 3x, so we've only got 14x, and we've got 49. And still having the plus 3x plus 22 still there. Now, this is useful because now we're going to still just work on this stuff and realize, of course, that that can factorize or even complete the square with it. And if we were to do that, we'd realize that we've just got x plus 7 all squared. And now it becomes a lot easier to see why the thing we're trying to prove is true, because now we can say as x plus 7 all squared is greater or equal to 0, as k squared is greater or equal to 0 for k any real number, then, that's a very dodgy real number symbol, then x plus 7 all squared plus 3x plus 22 must be greater or equal to 3x plus 22, because it's got to. And therefore, well, we've proven it. We've proven that x squared plus 17x plus 71 is greater or equal to 3x plus 22 for x is any real number. Right then. So that's a little more tricky one. Now, ultimately, those are all the skills you need. Just got another 3 more tricky examples to show you, just to point out, because sometimes these sort of things got to be a bit adaptable. So the first sort of example of this is if we have this one here. Looks a bit weird because you might notice we've got that greater than symbol rather than the usual greater or equal to symbol that we normally have in this case. However, that isn't an issue because, as you see, when we go through it, everything works out fine. If we complete the square with everything we have on the left-hand side, then we can quite quickly see that what we've got is, again, something squared. And then when we simplify that further, we've got something squared plus 5. Now that's really useful because we know that, again, x plus 2 all squared is got to be greater or equal to 0 because anything squared, you're getting sick of me writing this now, is greater or equal to 0 as long as we're dealing with real numbers. And then, therefore, x plus 2 squared plus 5 is greater or equal to 5. Therefore, x plus 2 all squared has got to be greater than 4 because 5 is greater than 4. And therefore, right then, and we've also got to be adaptable because so far all the ones I've been showing you have all been based on this similar idea of completing the square. But, although that's probably the closest thing you can have to a question that requires a particular strategy and approach, and that's why I showed the examples that way. You have to adapt and be able to just use the original fact I gave you, which is that something squared, if you're dealing with real numbers, has got to be greater or equal to 0, and maybe use that fact in other contexts. So if you look at this situation here, it is actually a very different problem because although you could complete the square with this question because it's a quartic with only x to the 4x squared, it's therefore, in theory, a disguised quadratic, I guess you could call it. However, if you were to complete square with it, you have to get rid of this later, but if you were to complete the square with it, you would end up with the following thing. And the problem is you can't really show that's greater than 20 using the justification we had before because we've got something squared, which is greater or equal to 0, plus 1, which is greater or equal to 1. Cool, but we're trying to show is greater than 20. And 1 is, of course, not greater than 20. So therefore, the way we approach this one is just realizing, of course, that x to the power 4 is equal to x squared all squared. Now that's really important because it means I've got a lot of things that have been squared in this original expression already. I've got the x squared all squared, which is therefore got to be a positive number because it's something squared. I've got another thing squared, which has also got to be positive, that's then being multiplied by 10, so it's got to be positive, added onto a positive number. So that stuff has all got to be positive, and then we're adding on 26. So we had something that was either 0 or positive with 26 added onto it. You know what? It's got to be greater or equal to 26, and therefore that's why it's got to be greater or equal to 20. So therefore, as x squared squared and x squared, 10x squared, let's say, are both greater or equal to 0, as k squared is greater or equal to 0 for any k that's a real number. Therefore, x squared squared plus 10x squared is greater or equal to 0. Very dodgy 0 there. And therefore, we had 26. We got something greater or equal to 26. And therefore, that's greater than 20. And so we can say x to the 4 plus 10x squared plus 26 is greater than 20 for x being a real number. So there we go, a different way of using that fact. I've not seen maybe directly a question like that before, but I'm just pointing out, you always have to be adaptable to these things, not just go, oh, it's a question I've seen 500 billion times before, and just repeat what you've been shown. And then the last of all, we got this one, which is, again, a bit of a different problem, partly because we're only dealing with x being positive, but it can still be any real positive number. So that's still decimals, integers, the whole lot. Okay, now this one is one that's a bit more tricky just because it looks more complicated. However, in reality, it's using a lot of the same skills we looked at before. Step one is I'd realize, oh, that doesn't look very nice, partly because we got two separate things. And what we've done a lot before is we've done factorizing and things like that, and it's difficult to do that in its current form. Something we could choose to do as well is we might want to have the 6 over on the other side. That's up to you, but if you do want to do that, remember to reuse the trick we showed before where we're not allowed to work on both sides really. So therefore, to get around that, we only work on the left-hand side by taking away the 6 that we would have got if we had worked on both sides, but then still only work on the left-hand side by adding the 6 back on. So we're only keeping the left-hand side because we've only added on 0. That plus 6, I'm therefore going to keep just hanging on floating for the rest of the problem. Because what I'm going to do is I'm going to combine all this stuff, and therefore we're going to basically do some fraction adding because we're going to create a common denominator of x and then combine everything together. So x written with a common denominator of x would be x squared over x. We've got the 9 over x still, and then minus 6 would be minus 6x over x. And then the plus 6 I said I wasn't going to absorb. That's interesting because then it allows me to obviously gather it all as the numerator of that fraction with the plus 6 added on. And that's very interesting because you might notice the top of that fraction factorizes very nicely. And now we've got all the things we need to be able to show that our original expression was greater or equal to 6, because we can now start by justifying that x minus 3 all squared is got to be greater or equal to 0, because anything squared is greater or equal to 0 if we're dealing with real numbers. And then, sorry that I mucked up that symbol there, didn't I? That should be a, let's rewrite it. That means we can start saying the next interesting thing, except this is where we've got to watch out. This has got to be greater or equal to 0, but only because x is positive. Because it's worth mentioning, if x was negative, x minus 3 all squared would still be greater or equal to 0, but x minus 3 all squared divided by x would be less than or equal to 0, sorry, if x was a negative number. So that's very important to point out, because it does affect how the argument goes, and that's why I've also got to point this out, justify it, because it's only because of this fact that what I said is true. Then that allows us to then go, wait a minute, if we add 6 on, it's got to end up being greater than 6. And therefore we can say that x plus 9 over x has got to be greater or equal to 6 if x is positive. Okay, there we go. That is a bunch of examples showing how you can approach these sort of questions, how you build up an argument to fully justify why the algebra expression, where you're allowed to plug in any x value you like, has got to be always satisfying the equality they're showing. So there you go. I hope you found that useful, and I'll see you in the next video.